200 pounds lighter than a Ford Flathead, 40 pounds lighter than Cadillac's V8, 100 million built. This is the story of the Chevrolet small block V8, an engine that started with just 162 horsepower and conventional pushrods, yet became the most successful power plant in automotive history. Picture this. It's 1953, and Chevrolet is hemorrhaging customers to Ford and Plymouth. Their ancient stove-bolt inline-six, dating back to 1929, is wheezing out 115 horsepower, while Ford's new Y-block V8 is making 130. Oldsmobile and Cadillac are selling V8s like hotcakes. Even Plymouth is working on a V8. Chevrolet's chief engineer Ed Cole walks into a meeting and announces they're going to build a V8 that will bury the competition. The catch? They have exactly 15 weeks to design it from scratch. The 1955 Chevrolet 265 cubic-inch small block V8 wasn't just another engine. It was a clean-sheet design that would power everything from grocery getters to Corvettes, from NASCAR champions to land speed record holders, surviving virtually unchanged in basic architecture for over half a century. While Ford would redesign their V8s 5 times and Chrysler would abandon their early Hemis, this little pushrod motor would soldier on, eventually powering over 100 million vehicles and becoming the most modified, most raced, and most beloved engine in history. To understand why Ed Cole's team was under such crushing pressure, we need to travel back to 1953. General Motors was in crisis mode. Chevrolet, once the sales leader, had fallen to second place behind Ford for the first time since 1927. The reason was simple: power, or rather, Chevrolet's complete lack of it. The Chevrolet Blue Flame inline-six was a tough, reliable engine that traced its roots back to the late 1920s. By 1953, it displaced 235 cubic inches and produced 115 horsepower with a compression ratio of 7.51. The power band was narrow, torque peaked at just 200 lb-ft at 2,000 RPM, and the whole thing weighed 625 pounds. Ford's new overhead valve, Y-block V8, introduced that same year, made 130 horsepower from 239 cubic inches and weighed about the same. But here's the kicker. Ford's V8 cost buyers only $165 more than the base six-cylinder. Customers were willing to pay for power. Meanwhile, within GM's own ranks, Oldsmobile's Rocket V8 was making 165 horsepower, Buick's Nailhead V8 was cranking out 164, and Cadillac's 331 cubic-inch V8 was producing 210. Even Pontiac was developing their own V8. Chevrolet, supposedly GM's volume division, was stuck with a six-cylinder that was essentially a modernized tractor engine. The problem ran deeper than just specifications. Young buyers returning from World War II and Korea wanted performance. They'd driven powerful military vehicles, flown in fighters, and experienced speed. The hot rod movement was exploding in Southern California. Drag strips were opening across the country. NASCAR was growing from regional moonshine runners into a legitimate racing series, and Chevrolet had nothing to offer these customers except reliability and economy. Ed Cole saw the writing on the wall when he became Chevrolet's chief engineer in 1952. Cole wasn't your typical Detroit executive. He was a genuine car guy who'd worked his way up from Cadillac's engineering department, where he'd helped develop their revolutionary overhead valve, V8, in 1949. He understood that Chevrolet needed a V8, and not just any V8, one that could be produced cheaply enough for the low-priced field, but sophisticated enough to compete with anything on the market. But here's where it gets interesting. Cole didn't just want to copy Cadillac's V8 and make it cheaper. He wanted to completely reimagine what a V8 could be. Working with a small team including Harry Barr and Al Colby, Cole laid out aggressive targets. The engine had to weigh less than 550 pounds, at least 75 pounds lighter than any competitive V8. It had to fit in the same space as the inline-six. It had to be cheap to manufacture, and it had to have massive potential for growth. The team started with the block. Instead of using traditional deep skirt design, where the block extended below the crankshaft centerline, they created a low block design with the block ending at the crankshaft centerline. This saved weight and material. The cylinder banks were set at 90 degrees for perfect primary balance. Bore spacing was set at 4.4 inches, wide enough to allow future bore increases, but narrow enough to keep the engine compact. Now here's where Cole's team got clever. Instead of using separate cylinder barrels pressed into the block like many engines of the era, they cast the cylinders directly into the block. This saved weight, improved cooling, and reduced manufacturing costs. The block was cast from high-grade iron with a tensile strength of 35,000 psi, allowing thinner walls without sacrificing strength. The main bearing caps were held by 2 bolts each, adequate for the initial power levels and cheaper than 4-bolt mains. The crankshaft was forged steel, not cast iron like many competitors. It featured 5 main bearings for smooth operation and durability. The journals were 2.3 inches in diameter, large enough for strength, but small enough to reduce bearing friction. The stroke was kept short at 3 inches, which reduced piston speed and stress while allowing higher RPM potential. Combined with the 3.75-inch bore, this gave exactly 265 cubic inches of displacement. The connecting rods were another masterpiece of efficient design. Forged from SAE 1038 steel, they measured 5.7 inches center to center. The small end used a pressed-in wrist pin bushing, while the big end featured precision insert bearings. The rods were shot-peened for fatigue resistance and weighed just 495 grams each, nearly 20% lighter than contemporary Ford rods. The pistons were cast aluminum with 3 rings, 2 compression and 1 oil control. Compression ratio in base form was 8.0.1, with optional power pack versions running 8.25.1. The pistons featured valve reliefs to prevent contact with the valves at high RPM, showing that Cole's team was already thinking about performance potential. Total reciprocating weight per cylinder was kept to just 1.8 pounds. But the real innovation was in the valve train. Cole insisted on push rods instead of overhead cams for cost and packaging reasons, but he wanted overhead cam performance. The solution was brilliant in its simplicity. The camshaft was placed high in the block, reducing push rod length and therefore flex. The push rods themselves were hollow chrome moly steel tubes, incredibly light but stiff. The rocker arms were stamped steel, held by individual studs that could be removed without pulling the heads. The valve springs were carefully tuned to prevent float up to 5,500 RPM, astronomical for a pushrod engine in 1955. The cylinder heads were wedge-shaped combustion chambers with inline valves, not the most sophisticated design, but easy to manufacture and effective. Intake valves measured 1.72 inches, exhausts were 1.5 inches. The ports were carefully designed for good flow velocity rather than maximum size. Cole's team spent hundreds of hours on the flow bench tweaking port shapes for optimal breathing. The result was heads that flowed 140 CFM on the intake side, not spectacular by today's standards, but excellent for 1955. The intake manifold was cast iron with equal-length runners to ensure even distribution. A single 2-barrel Rochester carburetor fed the base engine, while the optional power pack featured a 4-barrel Carter WCFB. The exhaust manifolds were also cast iron, designed for good flow while fitting in the tight confines of 1950s engine bays. Let me put that in perspective. In 1955, that was revolutionary efficiency. Ford's Y-block made 162 horsepower from 272 cubic inches, 0.596 HP per cubic inch. Plymouth's new 241 polyhead made 157 horsepower, 0.651 HP per cubic inch. The Chevrolet 265 with the Power Pack 4-barrel made 180 horsepower, 0.679 HP per cubic inch. Only Chrysler's 300 Hemi beat it for specific output, and that engine cost 3 times as much to build. But raw numbers don't tell the whole story. The small block weighed just 531 pounds fully dressed, 40 pounds lighter than Cadillac's V8, 50 pounds lighter than Oldsmobile's Rocket, and nearly 100 pounds lighter than Chrysler's Hemi. This wasn't just about bragging rights. Less weight meant better weight distribution, improved handling, and less stress on suspension components. It also meant the engine could be easily swapped into smaller, lighter vehicles. Initial testing began in early 1954 and immediately revealed the engine's potential. On the dyno, prototype engines were easily exceeding 200 horsepower with minor modifications. Test drivers reported the engine felt eager and responsive, completely different from the lazy torque of the old six. The short stroke meant it could rev freely to 5,000 RPM and beyond without the vibration common to long-stroke engines. By October 1954, the engine was ready for production. Chevrolet built an entirely new engine plant in Flint, Michigan, specifically for small block production. The plant featured the latest in automated machinery, including transfer lines that could machine a block in just 14.5 minutes. This level of automation was unprecedented for V8 production and allowed Chevrolet to price the V8 option at just $162, undercutting Ford by $3. The 1955 Chevrolet hit showrooms with two versions of the 2i65. The base engine with two-barrel carburetor made 162 horsepower at 4,400 RPM and 257 lb-ft of torque at 2,200 RPM. The Power Pack with four-barrel carburetor and dual exhausts made 180 horsepower at 4,600 RPM and 260 lb-ft at 2,800 RPM. But there was also a third version that would change everything. Enter Zora Arkus Duntov, a Belgian-born engineer who'd joined GM in 1953 specifically to work on the Corvette. Duntov saw the small block's potential immediately. For the 1955 Corvette, he specified the 265 with a special camshaft featuring increased lift and duration, raising the power band significantly. Combined with the four-barrel carburetor and dual exhausts, this version made 195 horsepower at 5,000 RPM. Think about that for a second. The same basic engine that powered Grandma's Bel Air sedan was making nearly 200 horsepower in the Corvette. No complex overhead cams, no exotic materials. Just good, solid engineering with room to grow. The Corvette version proved the small block wasn't just a passenger car engine, it was a genuine performance power plant. The racing community took notice immediately. Hot rodders discovered the engine responded incredibly well to modifications. A simple camshaft swap could add 30 horsepower. Porting the heads gained another 20. Multiple carburetors pushed power over 250. By the end of 1955, small blocks were showing up at drag strips across the country, often embarrassing much larger and more expensive engines. NASCAR teams were even more interested. The small block's light weight and compact size meant better weight distribution in stock cars. Its robust bottom end could withstand the punishment of 500-mile races. And unlike Ford's Y block with its complicated oiling system or Chrysler's expensive Hemi, the small block was simple to work on and cheap to rebuild. Smokey Yunick, the legendary mechanic and rule bender, called it the best damn engine anybody ever designed. Throughout 1956, Chevrolet continued developing the small block. Displacement grew to 283 cubic inches by increasing bore to 3.875 inches. The bigger engine came in multiple versions, from a mild 170 horsepower two-barrel to the legendary 283 horsepower fuel-injected version, achieving the magical 1 horsepower per cubic inch that marketers loved. The fuel injection system, developed by GM's Rochester division, was purely mechanical with no electronics, using a complex system of vacuum signals and mechanical linkages to meter fuel. It was finicky and expensive, but it worked. The 283 also introduced other improvements. The camshaft was redesigned with hydraulic lifters on most versions, eliminating valve adjustments. The oil pump was strengthened. The connecting rods were shot-peened for greater fatigue resistance. These weren't revolutionary changes, but they showed GM's commitment to continuous improvement. By 1957, the small block was powering everything in Chevrolet's lineup except the Corvair. It had become the go-to engine for racers, hot rodders, and custom car builders. Speed shops were sprouting up across the country selling hop-up parts. Companies like Edelbrock, Offenhauser, and Wyand were producing aluminum heads, multiple carburetor setups, and supercharger kits specifically for the small block. What made the small block so popular with modifiers? First, its design was inherently over-square, large bore relative to stroke, which is ideal for high RPM operation. Second, the 5 main bearings provided excellent bottom-end strength. Third, the wide bore spacing allowed significant displacement increases. Fourth, the simple pushrod valve train was easy to modify and adjust. And fifth, there were millions of them being produced, making cores cheap and parts plentiful. Let that sink in for a moment. While Ford was struggling with the oiling problems of their Y-block and Chrysler was pricing themselves out of the market with their complex HEMIS, Chevrolet had created an engine that was simultaneously cheaper to build, lighter, more compact, and had more development potential than anything else available. The modifications kept coming. In 1962, displacement reached 327 cubic inches through a stroke increase to 3.25 inches. This engine would power everything from Corvettes, making 365 horsepower, to Chevy 2 compacts, making 250. The 327 became legendary in its own right, powering many of the greatest muscle cars of the 1960s. Its 4-inch bore and 3.25-inch stroke created nearly perfect rod ratio geometry, allowing it to rev freely to 7,000 RPM with proper preparation. 1967 brought the 350, a 4-inch bore with a 3.48-inch stroke yielding 350 cubic inches. This would become the most produced version of the small block, finding its way into everything from pickup trucks to Camaros. The 350's combination of displacement, strength, and efficiency made it the perfect all-around engine. It could loaf along at 1,500 RPM in a truck or scream to 8,000 RPM in a race car. The big breakthrough came in 1970 with the LT1 350. This engine featured solid lifters, 11.1 compression, a radical camshaft, and free-flowing heads to produce 370 horsepower. More importantly, it proved the small block could compete with big blocks for power while maintaining its weight and packaging advantages. The LT1 dominated Trans Am racing, where displacement was limited to 305 cubic inches. But here's the kicker. While the small block was dominating on the street and track, it was also proving itself in the most demanding environment of all, endurance racing. Small block-powered Corvettes were competing at Le Mans, Sebring, and Daytona, often finishing when more exotic machinery failed. The engine's simplicity meant it could be rebuilt quickly during pit stops. Its efficiency meant less fuel consumption. Its reliability meant finishing races. The 1970s brought new challenges. Emission regulations and fuel economy standards threatened to kill performance engines entirely. Compression ratios dropped from 11:1 to 8.51. Camshafts became milder. Power outputs plummeted. The 1975 Corvette's L48 350 made just 165 horsepower, barely more than the original 265 from 20 years earlier. Many thought the small block's days were numbered, but Chevrolet engineers weren't done. Throughout the malaise era, they continued refining the design. Better cylinder heads improved efficiency. Electronic ignition increased reliability. Improved manufacturing tolerances reduced friction. By 1985, the tuned port injection system brought the small block into the modern era, with the Corvette's L98 making 230 horsepower while meeting strict emission standards. The real revolution came in 1992 with the LT1, not to be confused with the 1970 engine of the same name. This featured reverse flow cooling, where coolant entered the heads first before flowing to the block. This kept the heads cooler, allowing higher compression and more aggressive timing. The LT1 also featured computer-controlled sequential fuel injection, distributorless ignition, and roller camshafts. Power jumped to 300 horsepower, while fuel economy improved by 20%. Think about that engineering solution for a moment. Reverse flow cooling seems simple in hindsight, but it required redesigning the entire water pump, cylinder heads, and block cooling passages. The cooler heads meant the engine could run 10.51 compression on regular unleaded fuel. The cooler combustion chambers reduced detonation, allowing more aggressive ignition timing. It was brilliant problem-solving that extended the small block's life another decade. The swan song for the original small block architecture came in 1997 with the LS1. While technically a clean sheet design, the LS1 retained the same 4.4-inch bore spacing and 90-degree bank angle as the original 265. Now built from aluminum with coil-on-plug ignition, composite intake manifolds, and sophisticated port fuel injection, the LS1 made 345 horsepower from 346 cubic inches while achieving 28 mpg highway in the Corvette. But wait, there's more. The LS architecture spawned an entire family of engines that continues today. The LS7 made 505 horsepower, naturally aspirated from 427 cubic inches. The supercharged LS9 produced 638 horsepower. The latest LT5 with dual overhead cams and a supercharger makes 755 horsepower. All can trace their DNA directly back to Ed Cole's original. Designed from 1955, the small block's influence extends far beyond GM. When Ford finally abandoned their FE and 385 series big blocks in the 1970s, they developed the Windsor small block using similar design principles: compact size, lightweight, two-valve wedge heads. Chrysler's LA small block followed the same template. Even Toyota's UZ Series V8 and Nissan's VH-V8 borrowed concepts from the small block's architecture. So what was actually going on here? How did an engine designed in 15 weeks in 1954 remain competitive for over 50 years? The answer lies in Ed Cole's original vision. He didn't try to build the most powerful engine of 1955. He built an architecture that could evolve. The wide-bore spacing allowed displacement increases. The strong bottom end could handle boost. The compact external dimensions fit in any chassis. The simple design kept costs down and reliability up. Let's talk about the cottage industry that grew up around the small block. By the 1960s, hundreds of companies were producing aftermarket parts. You could buy aluminum heads that flowed twice as much as stock. Forged rotating assemblies that could handle 1,000 horsepower. Fuel injection systems, superchargers, turbochargers, nitrous oxide systems. If it could make power, someone built it for the small block. The crate engine phenomenon started with the small block. GM Performance Parts began selling complete engines in the 1980s, allowing hot rodders to buy brand new power plants direct from the manufacturer. This legitimized the hot rod industry and provided consistent, warranty-backed performance. Today, you can buy small block-based crate engines making anywhere from 195 to over 1,000 horsepower directly from Chevrolet. Consider the small block's racing legacy. It powered Richard Petty to NASCAR championships. It dominated Trans Am with Mark Donohue. It won IMSA GT championships, SCCA championships, NHRA championships. It set land speed records at Bonneville. It powered boats, airplanes, and even helicopters. No other engine has been successfully adapted to so many different applications. The human side of this story is equally fascinating. Ed Cole went on to become president of General Motors, the only engineer ever to hold that position. Zora Arkus Duntov became the father of the Corvette, transforming it from boulevard cruiser to world-class sports car. Smokey Yunick used small blocks to revolutionize NASCAR, finding creative interpretations of every rule in the book. These weren't just engineers and mechanics, they were artists working in iron and aluminum. The small block also democratized performance. Before 1955, if you wanted a fast car, you needed deep pockets. V8s were expensive options in expensive cars. The small block changed that. Suddenly, a kid making minimum wage could buy a used Chevrolet, bolt on some speed parts, and run with Corvettes. This accessibility created car culture as we know it. Cruise nights, drag racing, car shows, all built on the foundation of affordable performance. Here's something most people don't know. NASA used small block V8s in the 1960s to test spacecraft parachutes. The engines were mounted on sleds that accelerated test articles to supersonic speeds. Why small blocks? They were powerful, reliable, and could be rebuilt quickly between tests. When NASA needs absolute reliability, they chose the same engine that powered your grandfather's Impala. The military applications are equally surprising. Small blocks powered patrol boats in Vietnam, generating sets in Desert Storm, and specialty vehicles in Iraq and Afghanistan. The engine's ability to run on low-quality fuel, operate in extreme temperatures, and be repaired with basic tools made it ideal for military service. There are probably small blocks running in war zones right now that were built in the same Flint factory as the original 265s. Modern dyno testing reveals just how ahead of its time the original design was. A bone-stock 1955 265 block with modern pistons, rods, and cylinder heads can reliably produce over 700 horsepower naturally aspirated. With a turbocharger or supercharger, 1,500 horsepower is achievable. The original bore spacing, deck height, and bottom-end architecture that Ed Cole sketched out in 1954 had that much growth potential built in from day one. The restoration and collector community has embraced the small block like no other engine. Original fuel-injected 283s from 1957 can sell for $50,000. Numbers matching 327s and 350s are carefully rebuilt to factory specifications. But equally valuable are the stories. The drag racer who won his first trophy with a small block. The teenager who rebuilt one with his father, the family that drove across country in a small block-powered station wagon. Let's examine why the Pushrod design, seemingly antiquated even in 1955, proved to be an advantage. Overhead cam engines are theoretically superior. Shorter valve actuation path, ability to vary valve timing, potential for more valves. But pushrods offer simplicity, compact size, lower cost, and easier maintenance. For 99% of applications, pushrod engines provide plenty of performance. The small block proved that good engineering beats complexity every time. The manufacturing story is equally impressive. That original Flint engine plant produced over 100 million small blocks before closing in 1999. Think about that scale. If you lined up every small block ever built, they would circle the Earth 3 times. The tooling, procedures, and quality control developed for the small block revolutionized engine manufacturing. Techniques pioneered for the small block are still used in engine plants today. Environmental considerations eventually killed the traditional small block. By the late 1990s, emission regulations required precision that pushrod engines struggled to achieve. Variable valve timing, direct injection, and cylinder deactivation were easier to implement with overhead cams. But even then, GM's LS and LT engines maintained pushrod architecture while meeting modern standards, proving Ed Cole's concept still had life. The small block's influence on American culture cannot be overstated. It powered the muscle car era. It made NASCAR a national sport. It enabled the hot rod and custom car movements. It appeared in countless movies and TV shows. The distinctive small block exhaust note, that rumbling, burbling, slightly uneven idle, became the soundtrack of American performance. When people think of American V8s, they're thinking of the small block, whether they know it or not. Consider the economic impact. The small block created entire industries: speed shops, machine shops, racing teams, aftermarket manufacturers. Thousands of businesses and hundreds of thousands of jobs existed because of this engine. Cities like Detroit, Flint, and Daytona Beach were shaped by the small block's success. The economic multiplier effect of 100 million engines is staggering. Today, in 2024, you can still buy a brand new small block-based crate engine from Chevrolet Performance. The latest versions feature aluminum blocks, forged internals, and modern fuel injection while maintaining the original architecture Ed Cole designed 70 years ago. These engines power everything from restored classics to modern hot rods to race cars. The small block isn't just history, it's still making history. The technical specifications tell only part of the story. Yes, the small block was innovative for its time. Yes, it was well engineered and efficiently manufactured. But its true genius was in its potential, the ability to be whatever its owner needed. Economy car engine, check. Muscle car monster, check. Endurance racer, drag racer, marine engine, industrial power plant. The small block could do it all, and did. Modern engineers study the small block as a masterclass in design philosophy. It exemplifies the principle of perfection is achieved not when there is nothing more to add, but when there is nothing left to take away. Every component had a purpose. Every dimension was optimized. Every decision balanced performance, cost, manufacturability, and durability. It's the engineering equivalent of a Mozart symphony, seemingly simple, but actually profound. The small block also teaches us about innovation cycles. True breakthroughs don't come from incremental improvements to existing designs. They come from clean sheet thinking, from questioning fundamental assumptions, from having the courage to start over. Ed Cole didn't try to improve the inline six. He didn't copy Cadillac's V8. He reimagined what an engine could be and created something timeless. Here's the real kicker. In an era of twin-turbocharged, direct-injected, variable timing, cylinder deactivating complexity, there's something refreshing about the small block's simplicity. It reminds us that good engineering isn't about using the latest technology. It's about solving problems elegantly. The small block solved the problem of providing reliable, affordable performance, and it solved it so well that the solution lasted 7 decades. The collectors and enthusiasts who preserve small blocks aren't just maintaining machinery, they're preserving a piece of American innovation history. Every rebuilt 327, every restored fuel-injected 283, every numbers-matching 350 represents a thread in the fabric of automotive culture. These engines powered first dates, family vacations, racing victories, and countless memories. They're mechanical time capsules that connect us to our automotive heritage. Looking forward, the small block's DNA lives on in GM's current LT engines. While featuring direct injection, variable valve timing, and cylinder deactivation, they maintain the pushrod architecture and 4.4-inch bore spacing of the original. The latest LT6 in the Corvette Z06 makes 670 horsepower naturally aspirated from 5.5 liters, a specific output of 122 horsepower per liter that would have seemed impossible in 1955. Yet it's a direct descendant of Ed Cole's original design. The small block story is ultimately about vision, persistence, and the power of good engineering. Ed Cole and his team had 15 weeks to design an engine that would save Chevrolet. They created something that not only saved the company, but revolutionized the entire automotive industry. They prove that with clear thinking, solid engineering principles, and attention to detail, you can create something that transcends its original purpose and becomes truly legendary. When enthusiasts debate the greatest engine of all time, the small block Chevrolet V8 has to be in the conversation. Not because it was the most powerful or the most sophisticated or the most efficient, but because it was the most successful at what it was designed to do, provide reliable, affordable performance to millions of people. It democratized speed, it enabled dreams, it powered a cultural revolution, and it did it all with pushrods, 2 valves per cylinder, and good old American ingenuity. The next time you hear that distinctive small block rumble, whether from a restored '57 Chevy, a modern Corvette, or a weekend racer at the local drag strip, remember that you're listening to history. You're hearing the heartbeat of American automotive culture, the sound of innovation that refused to become obsolete, the engine that started with just 162 horsepower and somehow conquered the world. What's your small block story? Did you rebuild one in high school? Does one power your project car? Have you witnessed the evolution from carburetors to fuel injection to direct injection? Drop a comment below and share your experience with the most successful engine in automotive history. And if you enjoyed this deep dive into the small block's incredible 7-decade journey, make sure to subscribe, because we're just getting started exploring the engineering marvels that changed our world.